faces. Will the generated face match any real human as a whole? If the image is generated by any prompt or by the system, it doesn't match. But if I input the picture and try to generate another type of picture, it matches 90%. Then, if the picture matches 90%, what was the point of generating? Style. So you're styling the picture. That's a different thing. You're generating a face. That means it's maybe taking the eye color from somebody, eye size from somebody else, face color from somebody. So it probably learns from thousands of people to generate one picture. Does it make sense? So it's not going to have any one-to-one mapping with real input. It's not going to match any of the input directly. If it does not, you're safe. You're not violating it. Does it make sense?
Normally data set and real verification information data set as three data sets which are mathematically similar. The three data sets are basically data set.
Grounded on reality.
Now there's information
one match with any input. If it's a tabular data set, it's a text data set, maybe you're using somebody's name, another person's age, another person's height, and not exactly the value. It's maybe in your real data set it has a 5 height, 6 feet. Maybe after generation you have 5 feet. So this person's height decreased, another person's height increased. But all the relative, the mean, everything are similar. You generate that in many different ways. One of them is by using generative AI. You could do that. Previously, before generative AI, people used to generate synthetic data using other formulas or statistics, and none of these are perfect. Why are you doing this? To get away with privacy issues. Now, in order to generate synthetic data set, that is also going to be your CPU or GPU intensive. You need to run that parallel as well. We're not doing that here, but at least you see that this stuff is generating a synthetic data set. Okay. What is it doing? It is generating 100,000 samples with 20 features, and then it will try to classify. Fine. Now, if you go into the documentation of random forest classifier in scikit-learn, you'll find number of jobs parameter. So normally we are running only the function. We are not tinkering much with all the parameters. So let's see what does the documentation tell about this. Let's go to the documentation. Right. It does. We didn't even know because they didn't have time. Because most of the tutorial don't talk about this unless you're looking for specifics. Now, what's scary is what is the default value? None. What does none mean? How does the environment treat none? None means 1. So none means 1. That means how many ports are we using by default? Only 1, even if you have more. That's a wastage, right? You have them, you're not using it unless you want to save electricity. You might have a genuine case, but you want to save laptop battery. You have to do minimum learning while preserving battery. That's a different scenario. But in regular usage, we want to use all of them. The value for that is -1. Use all processors. If you use -1, it uses all of the available processors. Right? That is the desired one. Or leave just one. Otherwise, even if you have none, If the backend is configured to be work in parallel, then it parallelizes. It will depend on the other backend configuration. Is that okay? Okay. So coming back, we are specifying number of cores to use. So let's see. We need to measure time. How long is it taking? Is the font size large enough? Do we need to increase the size? Everyone okay with the font size? Okay. So I take that as yes. So it's a custom function with just for parameters, the checking number of jobs. So it's passing the number of jobs. So start time, the model runs, and end time. So you get your training time. Okay. So how long did it take to train? Okay. Let's see. So this is the shape, which is the dimension of the table. And it's measuring the performance of one core. How long did it take? 116 seconds. And before start, we said that all of the things that we are doing are working on just only one core. Because at one core, 25 core, 50 core, all but one core. Effectively means just one core. So what we are going to get is this comparison of running 4 times in a single core configuration. Does it make sense? So it took 1 second. Then we are asking again to use 25 of the core. 25% is same one core. So it should be, what is your prediction? How long is it going to take if you run this for one core again? Exactly the same, a bit less, a bit more. What is the prediction? It will take more time. Why? But this is effectively the same number of core. 25% of 2 core is just 1 core because we cannot use less than 1 core, right?
Maybe the priority is this.
There could be many different logic because we are using the system for longer. Maybe Google would deprioritize our class.
Overhead
We're not getting overhead in the sense because we are using only 1 core out of 2 cores. Okay, so this is one logic. It might get deprioritized because our tasks have been running longer. It's a shared CPU. You know, everyone knows that Google Colab is a shared CPU. So if other users are using a lot of resources, this will get deprioritized. Or less users using, might get a speed up. Like a shared internet connection, shared resources. There is no guarantee, but depending on it, go up and down. It could even speed up for another reason. You're running the similar task again, so we might get some cache benefits. It can get slower if the system is busier, or we are using it longer. It might become faster because we're doing similar task again. So something might be preloaded cache, something like that. Excellent. So it was 116. Let's see what does the second run take. So effectively, that's it's rounding up. So that's still 1 core, and we got 115.9123. We're printing 4 points after the decimal. 0.4f means 4 floating point digits in the floating point number. The 115.91, 116. So we got slightly less. Slightly less. Are you going to claim a speed up here? This is random difference. This much difference is insignificant. It could be due to random reasons. Even if we were using, say, 100 cores and you see 1 second improvement, it cannot be claimed because it could be random. Does it make sense? Not significant difference. So you cannot claim that. Let's see the third run. If you use 50%, that is still one core. So what is effectively that? We get 170. Now we are taking roughly 2 seconds more. So do you see the variation, how much it can vary? It's a single core running. So we are already getting a tolerance. Plus minus 2 seconds, already it can vary. So any measurement gives can be plus minus 2 seconds based on what you have observed so far. It could be much more, maybe 5, maybe 10 seconds. Okay. Let's run it for the fourth time, all but one core. It's going to mean still one core because 2 core, we're not allowing it to use the last core, so it's effectively again single core. What is your guess? How much time? So first time slightly decrease, then slightly increase. What is your prediction now? Compared to the first run or compared to the last run? So more than 117 seconds. It's exactly the same number of core, one core, always.
And the key improvement portion.
No change. We are running same code on one core for the fourth time. And
Yes, because we've already run the 2 times.
that's one logic. So some people are saying less time, some people are saying same time. So some people are saying nearby times, approximate the same time. Let's see. What does the fourth time say? So total cores minus ones, effectively one core, and that's 115.67. So you're back to the original run. So in average, 115 to 116. So average 116 maybe seconds. So roughly 2 minutes. Is that okay? If you look at the comparison table, so it's this data, it's being converted to markdown table for comparison. So in all scenario, we have used only one core. So the single core performance may vary slightly. Is that okay? And this was the cheapest CPU available in Colab. What if you use a more expensive core? So if you go to your Colab, and if you'd like to change your runtime, you have access for T4 GPU, the free ones, and the V5, this one. Okay. So I have not tried this T4. T4 is for you to try. We're going to use the tensor processing unit, TPU. And let's see how that changes things. So that TPU has, let's see how many cores. Again, exactly the same job being run. That is, run a classifier using different number of cores. This time, how many cores are going to be used? Let's see how many cores are available. We have 24 cores. Okay, in this tensor processing unit, we have 24 cores. So if you run this job, how many 25%, 50%, and all but one core? How many cores are we talking about?
6, 12, and 23.
6, 12, and 23. Is that okay with everyone? %25 of 24 core, 1/4. 6 cores are 24. So that's 6 core, 12 core, and all except the last core. Okay, so let's see. Okay, what is your guess? How much time would the single core run might take?
For the same data.
Exact data doesn't matter, but same size of it.
Take much less than.
Why? Why would the single core performance differ? Is it possible? One core. If you're using just one processor core, would a single core performance differ across different clusters?
Yes.
Why do you think so?
The different infrastructure, the core.
What you mean is architecture.
Architecture.
Yes. So architecture is one reason. Any other reason?
Clock.
Clock speed, the significant one. What is your base clock speed? The clock speed, and again, if it gets auto overclocked, so the clock speed, even if you have base, say maybe 1.5, and it is effectively 4 gigahertz, that is also going to make a difference. Even though it's one core, its speed might significantly vary. Just clock speed. And then again, somebody also said the architecture is different. So it could be much more efficient, more friendly to the workload. It could be workload specific CPU. So tensor processing units are more suited towards AI load, or also the Apple's processing units. So again, how different is the performance going to be based on our previous chart? Similar, a bit less, significantly less.
Significantly less.
How less? 90%, 75%, 50%, 25% of the time. So we are comparing two single cores. The previous one, free one, and this one.
That depends on the work speed and
What is your best guess? How much a single core performance is going to be differ? By 25%, 50%, 75%.
supposed to do it in 7 seconds.
Not 6 core. 1 core versus 1 core. We're not in 6 core yet.
Without knowing the processor, we can't say how much. Which processor we are using.
It's a 24 core TPU. Again, in both of the systems, we are not exhausting the memory. We are using, I think, less than quarter of the memory. So memory is not a bottleneck. It's just mostly the CPU or TPU. So any idea how much difference we might see? $75, $50, $25% speed up, say. 75% speed up. Ready? Same 100, similar 100,000, may not be exactly the same. 100,000 samples. And how much did we get? $76 or 77 seconds. What was the previous runtime? 116. So that's what, 60% of the previous time? Something like that? 60 to 70% of the previous time. So we got some understanding using a better CPU, single core performance differs. Okay. Now we are going to do what 25% of the core, which is 6 core. What is your estimate would be 6 core performance? You have done Amdahl. So what is your estimate? How many seconds 6 core going to take? Are you going to divide this by 6? Does that work like that? You cannot divide it by 6. Why? Why can we not divide it by 6? Because there is a limitation. A job has sequential part and parallelizable parts. So speed up is not linear. So in that case, what is your estimate? How many seconds might it take for a 6-core run of the same task? That took 77 seconds in this TPU. 35, you're going 35. Anybody else? 35 seconds. Anybody more? Anybody less? More optimistic? 50 seconds? That's pessimistic. Okay, so 35 and 50. Anybody less than 35, more than 50, or somewhere in between? In between 35 and 50?
Also,
Anybody less than 35? Or more than 50?
no.
Is it likely to be more than 50? Can it increase? Is 6-core performance, can that increase from 76 seconds, 77 seconds? It's not going to significantly increase, that's for sure. It can slightly increase if the task is not parallelizable because of the random behaviors. Slightly increase. If the task is not parallelizable at all. If it's a bit parallelizable, it's going to be slightly decrease. If it has some portion parallelizable, it's going to decrease by some amount. So let's see. How much is that? 20 seconds. We are rapidly progressing towards 0, right? How many cores do you think are needed to reach 0 seconds?
If there are sequential parts, we won't reach it.
If there are sequential parts, not possible. Okay. Depends. Yes, the ratio of sequential and non-sequential parts, that's so amount of dependency there. The parallel part, you can use maybe 1,000 core or 1,000,000 cores to significantly reduce effectively less than 1 second. So almost 0 second is possible for the parallel part because you can use 1,000,000 core in a supercomputer on a large cluster. Okay. So with 6-core, we are getting 21 seconds. What is the next cutoff? 12-core. So from 1 core to 6-core, we got 20 seconds. 1 core to 6-core, we got 20 seconds. What do you think the next jump is going to be? 20 seconds to what?
5 weeks or less.
5 seconds or less. We are very optimistic. So world is looking green. Anybody else? More optimistic.
Or it might be capped because of the non-parallel parts.
5 seconds. 5 seconds. Anybody more? Anybody less? Good to see people are counting fingers. Very good approach. Let's cool down the processor a bit. No opinion?
13, 14.
13, 14. 13, 14, 18. We got 5, 13, 14, 18. Okay, before I lose track, I need to write that down. We have 5, 13, 14, 18. Okay, Sarah, do you see the screen now? Sarah Milham Zaman? Thank you for confirmation. Okay. So we got 5, 13, 14, 18. 18, so that's very close to 20. 5, 13, 14, 18. So nobody between 5 and 13 or less than 5. Okay, any other guesses? Online people are proceeding with caution. 50% of the core, half the machine going. What? How is it possible?
Yeah.
Yeah.
It's good to dream. We're hoping, and we're almost sure, right? 6 core got a lot of victory, right? This time we're supposed to have a total victory. But there is 20.56. We got slight increase, right? So the overhead, a bit of overhead or some random deviations. So 20 seconds, still 20 seconds with a bit more, 0.2 second more. Now we are getting very worried. If 6 core to 12 core slightly increases, which is insignificant, it could be just random deviation. There are other things like processor scheduling things, other variable, that's a shared machine. What do you think all but 1 core, which is what, 24 minus 1, 23 core, what do you expect to see?
We can overkill because we can see clearly that it's not going to be.
First, okay, so one opinion is overkill. Why?
Because you can always see that the time has been capped for 6 to 12 already.
Very logical. Then we already see that 6 core to 12 core didn't make much difference. Rather, it sometimes could be random deviation to slightly increase. So we give up, right? If 6 extra core could do nothing, what do 12 cores do? Not 12, 11 more do, right? Exactly the same thought was thought by statisticians, all the AI people, before the LLM. Because you keep feeding out data, the performance curve starts flattening. And then when massive amount of data was given, then started to show some signs of intelligent behaviors, right? So then the LLMs come. It went beyond expected statistical response. So everybody gave up, right? Any hope left?
So for the improvement to happen, we have to give a lot of data. We are currently not doing.
All we have is 100,000 samples, the same data. We are comparing with the same input configurations. Okay, anybody hopeful? Anybody feel like having dinner anymore? What's going to happen? What's going to happen with 23 cores?
I think no change.
No change. Already given up. No change.
The code doesn't really.
Time might increase, not just losing hope, also thinking very pessimistic about it. I don't trust TPUs anymore. Anybody else? 21 seconds. Then you're on the safe side. Also has a logic. Maybe you have more overhead. You're managing more processor, more data exchanges, maybe, right? So more switching things around, which has some overhead. That's logical. Anybody else? So some people say somewhat same, some people say slightly increase. Anybody for decrease? No? The winter has come. Take a deep breath. 25 seconds. Which is using 11 extra cores, we have gained 5 seconds. I was being hopeful, maybe slight decrease. It could mean another thing. Maybe that's overhead. It can mean another thing as well. Maybe it's overhead as well as maybe things can vary by 5 seconds. If you reach the limit, things can vary by 5 seconds, which might mean 5 seconds of difference might not mean much. It could be in your random deviations. It could be overhead or a combination with your random differences. So, if somebody got 1 mark more in any exam, doesn't mean they're significantly different, right? So here we got, what about the steps? 20 seconds, 70 seconds like that, 160 seconds we got. So what up to what to be significant difference, that's another measure. Okay? So your job is to play like this with different algorithm and see if we can find out more speed up in any of the algorithms. Is that okay? Using any of the CPUs, you might need to use multiple accounts for free accounts to see what's possible. You already have 2 accounts, right? The Gmail one and the G Suite one. You could try and see if you can see significant. We have reached something. Do you need the notebook or can you do it yourself? Okay, so if I don't share it for today, please ask in the classroom. Okay. What is your task? Practice task. Try different algorithms and find out which one or ones provide significant speed ups in number of cores. Maybe another algorithm will behave more higher core count friendly. Second task is to read upon this job lib. Job lib, this is
documentation.
This is a documentation, right? So this is job lib. How is it improving things? Okay. So this job lib part is not optional. So go through this job lib documentation, try to understand what it is. Again, you don't have to write codes, but conceptual. Okay. Now, attendance is not being taken in there, so don't post in classroom chat, it will get lost. Do you take attendance today? No. You have the quiz.
Oh, then
Is there anyone who is present but chose not to submit the quiz? Anybody? Okay. Now the next question is the midterm. When is our midterm? 16. I have a question to ask to 7 or 6 people. 7 or 6 people. 7 or 6 people. So we have 2 slots. 40 minutes each. 7 or 6 people would so duration is 40 minutes, okay? So this is a question for only 7 or 6. Which one is better, 2 p.m. or 2:50 p.m.? Everybody write in the chat, please. We got 2 each. This is offline. Good question. Restart, restart. Offline, in person. In person. So this is in person. So in person again, 2 p.m. So we are restarting. Everybody repost. 250 versus 2. We got 3, 4, 5, 6 to 50, 7 to 50, 8 to 50, 9 to 50. We still are looking for more than 15 responses. 10 to 50. 10 to 50, looking for some more. In person, 7 or 6. Who are 7 or 6 here? Anybody 7 or 6? Nobody? 250. Okay, so I think it would be more convenient for most people if we do 250. So we would seek the kind collaboration of 2 p.m. people. So let us sacrifice for them. Thank you for understanding. So 76 is G50 and rest of you is 2 p.m. to 2:40. Is that okay? 2 p.m. to 2:40. Where is it? 7H30C. 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 When? 16. That means the time. Now, what to do about the syllabus? Yes. Most likely wrong. Well, sometimes parallelism can go really long. To share something. If you see, if anyone has any explanation for this, do it well. Data corruption can happen. Parallelism gone wrong. So, what do you see in front of you? Lecture 4.5, right? It's in the lecture folder. And there is another folder, lecture 4. Inside lecture 4, we have the file edited last week discussion, November 2nd. That's lecture 4. Okay? And if you do lecture 4.5, which was just created, that's empty. Which one was created today? 4.5. Let's rename this. Lecture 5. Done? Okay. Opening lecture 5. It was created today. Was it blank folder?
Yes.
Yes. Let's open this. It's still blank. Okay. Go to lecture 4. It has files. Good. So I moved things around a bit and was finding any change done to the latest folder was happening to both of them. I did not make any change in that folder. Still, CC last modified is November 2. But here it shows this back. Under a different user account. Okay. So let's get the syllabus. So I have seen my own emails sent in 1970 in Google Groups. 70 or 69. That's not the issue. The issue is that is before birth of Google. It was before birth of Google. How could someone have sent an email using Google products in 1970? So it's some threading gone wrong. Maybe all threads were not updated. The date synchronization, because it's first gets created using the default value state, which is the earliest system time. So we have seen what? We have seen single core CPU performance variations, and then single core CPU versus TPU performance. Then multi-core speedups, multi-core variations, multi-core overheads. Okay, so what we have is so there are different laws and their maths.
Math paper review on search summary. That we have math one good.
Let's see.
People will understand.
How many papers did you submit? Paper reviews? Aren't you supposed to submit 2? Before mid 2, right? Anybody submitted both? Anybody? First and second paper review. Both? Anybody else? Both? Which one is easier, 1 or 2? So, can you comment which one was easier, paper 1 or paper 2? So, I got 2 votes of paper 1 being easier. I got 1 vote, paper 2 was being easier. Okay, now it's 50-50. Anybody else? No, we have 2, 3. 3 people thinks paper 2 was easier. No, it's 3-3. Quickly, we are running out of time. We have a few minutes left. Quickly, or it's overtime. So, which one is shorter? It's 10 pages and 9 pages. Any other votes? Final chance. The class seems divided. Okay, so you have paper 1 then. Since more people have read it, right? So paper 1 wins. All right, any questions? Yes, lots of them. No. It's based on laws. The maths are not from papers. If it's basic, then yes.
Summarize papers for you. Do we have something?
No, 25.
Portion of the everyone's sorting, searching.
Right. Oh, is it 25 or 50? Let's see. I have a question. Are you good with algorithms? Would you choose between remaining 25 pages from there versus the review paper 1? Which one would you like? Review paper 1. Okay, done. So it remains as is. Okay, anything else? So I hope all are able to answer the questions. Any other questions? In the lecture files, if you go through the discussions, those pages has laws and other algorithms. So if you go through these, you'll find the formulas. Okay. And along with examples, and some of the slides may also have examples. So practice those. Any question?
What about the paper summarizing?
Does that explain that? Okay. So, but the quizzes after midterm may include those. Is that okay? And within this, all the pseudocodes, make your own version. Even if you don't do line by line, make your own version, whatever you can remember.
Look what's the example. So, we get about this.
Because in real life, you'll be coding with reference in front of you. So memorizing is not needed. If you get the concept, that's fine. So we're not asking for what would be the lower bound. Okay, thank you. Allah for the
The course would have to be enough.
Try to take the exam right
in
midterm.
conversion.